This is lecture 6 for week 7 of CS 1030. And in this lecture, we're going to switch gears. We're not talking about number systems anymore. We're going to talk about a different aspect of data representation, which sort of builds directly on stuff we've previously talked about, but it's going to be a change of topic. So let's talk about representing text first. Okay, so far we've just shown using fixed width binary numbers to represent integer numbers, but of course, there's a lot of other things that we'd like to represent using digital data. We could use them to store colors, sounds, images, movies, computer game characters, documents in word processors. There's a huge amount of things that we'd like to actually represent in a computer. And now we're going to sort of start to talk about how we can make that happen. So one of the simplest things to represent is text. So a text document is composed of individual characters, and the way we represent the characters is basically to have the computer stores binary numbers that represent, that are used to store which character it means. And so let's talk about how that works. So how do we do that? How do we, what characters do we represent? What languages can we deal with? And so what we're first going to do is talk about some simpler ways to represent text. And then sort of at the end of this lecture segment, I'll talk about how we represent text for real on modern computer systems. So what we need is to assign every character that we want to show on the screen, we want to give it a binary number. And so here's one example we could have done. We could have said that the letter A is represented by the 5-digit binary number 00000. F could be 1, H could be 2, etc. And if you look at this, you think, well, first of all, we're not representing the letters in order, so that might not be a very, sort of smart idea. And second of all, if we're only using 5 binary digits to represent each character, the total number of characters that we can represent in this system is not very many. And maybe this isn't a very good idea. So let's look at one of the numbers that actually, one of the systems that actually is used in practice. So this is called the ASCII character set. It's an abbreviation for American Standard Code for Information Exchange. And this is not at all the first character set that was ever designed to store characters in a computer, but it's one of the ones that was sort of dominant for a long time. It's no longer the dominant one, but it was, it was commonly used for a number of decades. So in the ASCII system, characters are represented using 8-bit numbers. So that is to say, we use 1 byte to represent each character. And so a question we can ask then is, how many different characters can we store in an ASCII document? And well, since there are 8 bits in a byte, there are 256 different values that can be stored in a byte. We can represent 256 different characters. And here I've linked to an online ASCII chart. I'll show it on the next slide, but I linked to it so you can sort of get the high-res version. So one thing that's nice is that both uppercase and lowercase letters are stored in order in ASCII. And that's good because if we want to do something like sort words by dictionary order, then the sorting task is made easier by the fact that the letters are stored in order in the underlying representation. So let's look at this. So here's an ASCII table. So for example, if we want to look at what how a capital A is represented in ASCII, it's represented by the character, or it's represented by the number 65, of course, stored in binary, which in hex is 41. So another one, like lowercase z, that's represented by the byte storing the value 122, which in hex is 7a. And so what all can we store in ASCII? Well, we can store the uppercase English letters, the lowercase ones, some punctuation, and then there's some sort of out-of-band stuff. This is sort of terminal control things used to do things like make a sound on the terminal, or go to the next line, and some other stuff like that. So now the problem with ASCII is it's really basically completely useless for representing documents in, for example, Chinese or Arabic, or any other language than English, really. And so ASCII has sort of it's basically fallen out of favor as the preferred representation for characters. And what we use now is a system called Unicode. Unicode is a very versatile, very powerful way to represent data, and it supports over 1 million different things called code points, and code points represent characters. And the nice thing is if we have such a large number of characters, we can not only represent the letters that we use in English, we can also represent the characters that we use in Japanese, we can represent the characters that we use in Arabic, we can represent a lot of different languages, and basically that's what we do. So when you look at documents on a modern web browser, it's loading Unicode and rendering that Unicode, and this is basically what allows us to transmit and represent documents in a whole lot of different languages sort of easily and conveniently. So something that's sort of confusing about Unicode is it has different encodings. There's not just one, it's not sort of just one system, it's kind of a family of systems for representing text. And the most common one, the one that you see most often, is one called UTF-8. And UTF-8 is sort of interesting in the sense that it's a variable length encoding. And by what that means is that a single character that you see on the screen might not be represented by the same number of bytes as the character next to it. And so some characters are represented in UTF-8 using 1 byte, others take 2 bytes, and others take 3 or 4 bytes. And one of the kind of nice things about it is commonly used characters, like the ones that we can represent in ASCII, use fewer bytes. And in fact, all of the ASCII characters, or most of the ASCII characters, use only 1 byte. And then things that are represented, that are used less commonly on, sort of in typical usage of computers, might take 2 or 3 or 4 bytes. And here I've linked to an online Unicode chart. You can click on that and take a look. Unicode is sort of pretty complicated and pretty cool, and it's basically taken over the world. And so here is a graph produced by Google. And what this graph shows is across a number of years, and unfortunately the graph stops in 2012, but it shows over a number of years, sort of the early part of the 21st century, the popularity of or the percentage of web pages using different character encodings for text. And so you can see, for example, that in 2001, ASCII documents were close to 60% of the web, and by 2012, that had dropped to below 20%. There's some other encodings that we don't really care about that much, but the one that I'd like you to take a look at is UTF-8, the one we just talked about, the Unicode family that sort of is the most common one, was essentially at 0 until after 2002. And now it's above 60%. And if this went out to 2020, I expect this would be up to 90% or 95% or something like that. Thank you.